Okay, today I would like to cover uh, power and efficiency. And so with power and efficiency, there are some things that you should know based on your learning objectives. And so for our learning objectives today, you should be able to identify the power quantity expressed in base SI units. Also convert from one unit of power to another. So that'll come from your conversion equation sheet in that little box on the conversion equation sheet. And then you're going to want to be able to define power. And then given that power is equal to energy over time, from those, you want to be able to determine a final quantity given two of the three things, either energy and power, combination of power and time, so then you'd be finding energy. Or if you have energy and time, then you'll be finding power. And then for chapter 8.10, you'll want to recall the limits of efficiency. So efficiency can only be between 0 and 1 or 0 and 100%. And we'll go over that a little bit further. Explain the following terms in relation to efficiency. So what is power input, power loss, and power output, and how do they relate to the efficiency of a motor or a device of some sort? And then again, given three of the four quantities, energy, power, time, and efficiency, be able to determine the final quantity that you do not know. Given our two equations of power equals energy over time, and our efficiency is equal to our power out divided by our power in, or you can also rewrite that equation as power out is equal to efficiency times our power in. So here, when we look at the relationships between power, energy, and time, we know that power is equal to energy over time. So P equals E over little t. And then for efficiency, our second equation is that our power in is equal to our power out plus our power lost in a device outputting power. But our power out is equivalent to our efficiency times our power in. So when you have your power in, it's what is required by the device to operate. So usually this is what is required when you plug a device into the wall. How much wattage does it take to power that device from the wall in order for it to operate? And then your power out is what power goes out of the device in order for it to work. So if this is a motor, then your power out is whatever that motor is doing, whether that's lifting something or pushing something, moving something, or creating thermal energy of some kind. And then your eta, which is your efficiency, is the measure of loss during the process. And so this is going to be your power lost by your device, either in the form of thermal energy or some other form of energy loss during its use. And so our efficiency is usually measured between 0 and 1, being from 0 to 100%, our percentage being represented as our decimals. So eta, that Greek letter, is the little funky N, represents our efficiency in our equations. And then we know that our input power is always greater than our output power, because in order to get the power out of a device, you're going to multiply your efficiency of that motor, or your device cannot be greater than 100%, times your input of what your device requires to use. So if we have a device that is 67% efficient, and it requires 120 watts, we can take that 0.67, representing our 67% efficiency for our eta, multiply it by our power in of 120 watts, and then get what is output power for our device. So in this intuition check, we want to know what is the efficiency of this motor. So if I say that the power in is 100 watts, that we have a power out of 75 watts, and then we have a heat loss of 25 watts of power in our device. So our power in at 100 watts and our power out at 75 watts. If we know that P out, so here we have our P out, so we know P out is equal to our eta times P in. So then our eta is equal to, and I'm just going to do P with a little O over P with a little I for in. So in that case, 75 watts over 100 watts will give us an efficiency of 0.75 or 75%. So here in our example, we have a 75 kilogram load, and it is raised as high as possible in 30 seconds by 150 watts, 75% efficient motor. So how high in units of feet can this load be raised? And so in this case, we start with our problem statement, so using process. So our problem statement is we want to find the height that we lift this object in feet. So I have my height represented by my symbol H, and then are my units of feet in my problem statement. When I represent the problem here, so if I look here, I have my representation of the problem. So I've got my little box, then I have my height here, represented by my up arrow with my little h. When I organize all my information, I know that I have a mass of 75 kilograms, a time of 30 seconds, a power of 150 watts. Then in reality, this is a power in of 150 watts, an eta of 75%, so I can then calculate my power out. And then I know if I'm lifting something, I'm going to have potential energy. So where potential energy is equal to my mass times my gravity times my height. And then I have my gravity, which is my assumption here. I have my power equation, and then my P out is equal to my eta times P in. So now I can move on to my calculations in this problem. So the first step is to determine the power input required. And so, or power output required. So I have my P out is equal to eta times P in. So I input my values that I have, 0.75 for my eta, my efficiency, which is unitless, times 150 watts. So my power out for my device is 112.5 watts. Then I can determine my energy required. And so that energy required, if we use power is equal to energy over time, rearrange our equation to find our energy, and know that our P is equivalent to P out, then we can input the value of 112.5 watts for my P, 30 seconds for my time to get 3,375 joules as the energy required to lift my object. And then from there, I can determine how high the mass is lifted by rearranging my potential energy equation and using that for my energy, setting it equal. So when I solve for H, I get energy is equal to, H is equal to energy divided by my mass times gravity, which is 3,375 joules divided by 75 kilograms, which is multiplied by 9.8 meters per second squared. So I get a total height of 4.5918367 meters. And then I need to convert this into feet. So when I evaluate my solution, I know that 15 feet is not high. It's approximately 2 stories in a house or a building. So my motor is only 150 watts, which really isn't that much power. So 30 seconds is reasonable to lift this 2 stories high at 75 kilograms. So now, as kind of a concept check, if I have this same 150 watt motor that is 75% efficient and use this to raise that 75 kilogram load 15 feet in 30 seconds, if we double the distance, we want to lift it. So we want to go from a 2nd story window to a 4th story window. How long will it take for the same motor to accomplish this task? So I've given 6 choices here. A is 60 seconds, B is 37.5 seconds, C is 30 seconds, D 34 seconds, E 15 seconds, or F 6 seconds. And so if we look at our 2 equations, we have our power is equal to energy over time. And we know that our potential energy is mass times gravity times our height. So if we take this height and double this, it means that our energy doubles. So then what happens? To our time, well, if our energy doubles, then our time must also double. So for our second example today, a 5 horsepower, 75% efficient motor is used to raise a container 10 meters. Assume that container is full of bromine and the specific gravity of bromine is 3.12. The container has a mass of 500 kilograms. How long does it take the motor to accomplish the task in units of seconds? So in this case, we're assuming that the total mass of the container is the container containing the bromine. And so that second sentence, the fact that it's even full of bromine and that the specific gravity of bromine is 3.12 is information that we really don't need in this problem. So all we need is the mass of 500 kilograms. So we want to know how long does it take the motor to accomplish this task in units of seconds. And so take a minute to work this out. For my problem statement, I want to find my time in seconds it takes to raise this load. So again, I use my same representation of my problem, this time where I'm looking for my time in seconds. I have all of my given information where my P in is equal to 5 horsepower, my eta is 75% or 0.75, my height is 10 meters, mass 500 kilograms, my potential energy is equal to M times G times H, where M is my mass, G is gravity, and H is my height. My gravity, I'm assuming this is on Earth, so it's 9.8 meters per second squared. And then my power is equal to energy divided by time, and my power out is equal to my eta times my P in. And so my first step is to determine the potential energy of lifting. So I calculate my potential energy given the mass, the gravity, and the height that we are lifting this. And since everything is already in metric units, it's very easy to come out with an answer in joules. So I get 49,000 joules as my potential energy. So then I needed to determine the power available to lift. So given that I have a 5 horsepower motor, which is what it's rated at or requires to operate, I can calculate the power out that will be used to lift the object. And so I have my 0.75 times my 5 horsepower motor, but we've got to convert that horsepower into watts in order to get out into metric units. So I end up with 2,798.507 watts as my power out. And then from there, I determine the time taken to lift the object. So my power is equal to energy divided by time. I rearrange my equation to find my T, time. So when I do 49,000 joules divided by however many watts it is, from step 2, I can find that my time is 17.5093362 seconds. And given that this is a 5 horsepower motor, which is usually used to move smaller boats, which are heavier than what we were using within our last problem, it should take the motor a little bit less time to lift this 3 stories instead of the 2. So our time seems to be reasonable at 17.5 seconds. So now for the rest of class, what I'd like you to do is to break out into your problem solving groups. So we're going to send you out in breakout groups where you can work on the 3 problems that are posted on Blackboard. And so if you need to find those, go to the announcement where I have the agenda for today's class, and you will find the folder that also contains the problem solving session in a PDF form. If you have any questions, you can always attend my office hours on Monday from 1 to 3, Tuesday from 1 to 3, Friday from 10 to noon, or 1 to 3 p.m. I will see you soon. Bye.